Hello, my name is Olivia Martin, and this is my Physics Lab 5. In this video, I'll be walking you through my computational physics investigation where I modeled a collision between a teenager on a swing and a toddler walking in front of it. We will look at how I animated the motion using real data, calculated force, velocity, and work, and discussed uncertainties and approximations, just like in previous physics labs. This investigation is rooted in several core physics concepts, including momentum conservation in inelastic collisions, impulse and force calculations, and work energy principles. I focused on how motion data can be used to simulate and analyze collisions using vector physics. By tracking the position of both the teenager and the toddler before and after the collision, I was able to calculate velocity vectors and applied the principle of conservation of momentum. Because I assumed an inelastic collision, I treated the teen and toddler as a combined system immediately after impact. This means the final velocity is shared between the toddler and the teen, and we can calculate how momentum was transferred. Next, we use that velocity change to determine the impulse, which is the product of force and time. This gave us an estimate of the force the teenager exerted on the toddler during the brief moment of collision. Finally, we applied the work energy principle by calculating the work done by the toddler using the dot product of force and displacement. This tells us how much energy was transferred to the toddler during the impact, which helped explain the change in their motion post-collision. This blend of theoretical physics and data-driven simulation helped us bridge real-world video tracking with classical mechanic concepts. The code is written in GlowScript and begins with loading corrected position data for both the teenager and the toddler. Here's how the code aligns with physics. The spheres representing the teen and the toddler have their radius scaled proportionally to mass and scaled up 5 times for visibility. We used make trail equals true and retain equals 10 to keep a short visible trail of motion. The animation rate is slowed to real time using rate equals 10. Velocity is calculated by the change in position over a small time interval. The magnitude of the final velocity and the magnitude of the force applied by the teen on the toddler are calculated. Work is computed using the dot product of force and displacement, and the magnitude of the toddler's displacement after the collision is also calculated. The simulation closely mirrors the overall motion seen in the original video. The teen's swing motion follows a realistic arc, and the toddler's walking path is faithfully recreated using the position data. When the collision occurs, the model calculates and visualizes key physical outcomes, such as the final velocity of the teenager before impact was calculated using the change in position and time, giving insight into the teen's momentum. The force the teenager exerted on the toddler was derived from the impulse momentum theorem, producing a measurable vector quantity. Work was calculated using the dot product of force and displacement, revealing how much energy was transferred to the toddler during the collision. And the displacement of the toddler post-collision gave a clear indication of how much the toddler moved due to the impact. These calculations were printed in the console as magnitude values, helping to quantify the severity of the impact. While the model assumes an inelastic collision, the fact that the toddler moved significantly after the collision, visually and numerically, reinforces the idea of momentum transfer and physical consequences in the interaction. There are several sources of error and approximations, such as the motion of the recording was non-steady, leading to tracking inaccuracies. The viewpoint was taken from the ZY plane, so it was harder to track the points. The point of mass from tracker was taken from points of contact, not the center mass. The mass scaling in the visuals is for display only and does not affect the calculations. Real-world friction, air resistance, and body compliance were not modeled, and we assumed a purely inelastic collision, meaning no bounce. In an elastic collision, both momentum and kinetic energy are conserved. Unlike the inelastic case, where the teen and toddler stick together and share a common final velocity, an elastic collision would result in the two objects rebounding off each other with separate final velocities. The teenager, being more massive, would likely retain a larger portion of their velocity, while the toddler would be pushed back with a greater change in speed. This will also allow us to calculate the initial and final kinetic energies of both participants and confirm that the total energy before and after the collision remains constant, aside from negligible losses. Observing an elastic version of this collision would help us better understand how energy and momentum interact in real-world impacts, especially in systems where rebound or bounce occurs. In summary, this investigation tied together motion data, vector physics, and code-driven modeling. While approximations and uncertainties exist, the simulation helped us visualize and understand the physics of real-life motion and impact events. Thanks for watching.